Hi everyone, my name is Makumba Gerard of EduMath. In today's video, we are going to look at the Newton Raphson method. But before we continue, subscribe to EduMath such that you can be notified of the new videos that we make every day. Let us get straight into it. See you there. So under Newton Raphson method, if xn is the initial approximation for the root of the equation fx equal to 0, then a better approximation xn plus 1, remember these are subscripts, they are subscripts, can be obtained from the expression xn plus 1 equal to xn minus fxn divided by f derivative of xn. So this is what we are going to base on if at all we are given the initial approximation. The better approximation can be found using that formula, where this n takes on 0, 1, 2, 3, 4, and they continue. Now before we continue, you have to note that the maximum error is given above. Maximum error is equal to a half times 10 power negative n, where that n is the number of decimal places. Yes, this is very important because we are going to, before we continue, have to find out the error. Just don't worry about this. Right now it is going to look very new to you, but you will like it. So we are going to deal with the Newton Raphson method here. Let's have an example. Given the equation x power 3 minus x minus 1 equal to 0, Roman numeral 1, locate where the root lies. Roman numeral 2, use Newton Raphson method to find the root correct to decimal places. This is very important also. Solution. First of all, we have to locate where the root lies, and that's what is required of us first. So we say let fx to be equal to 0. So if fx is equal to 0 and this is also equal to 0, that implies that fx is equal to x power 3 minus x minus 1. Then we need to locate where the root of this equation lies. Like we saw previously in the previous examples, we shall discover where the root lies by trial and error method. And we pick on values which are in the neighborhood of 0. So I will pick on the domain. Our domain x will be lying in or having values like 0, 1, 2, 3, negative 1, negative 2, negative 3. Let's try out those ones first. If we happen to get sign change, okay, then we shall have to, conclude that there is a root. So I'm going to start by getting f of 0. Put here 0. We shall have to get negative 1. F of 0 there. You get negative. Let me get f of 1. F of 1, put here 1. I will get still negative 1. There is no sign change here. Negative, negative, no sign change. Let me go to f of 2. Put here 2 power 3, that's 8. 8 minus 2, you get 6. 6 minus 1, you get 5. So there is sign change here. There is sign change there. And therefore, since f of 1 times f of 2, when you get this times that, negative 1 times positive 5, you will get a negative 5, which is less than 0. Then there exists a root between 1 and 2. So we have a root existing between 1 and 2. Now we have discovered where the root lies, or we have located where the root lies. So we are through with the first part. We need to go to the next part where we use the Newton Raphson's method. Newton Raphson's method. So this was Roman numeral 1. Roman numeral 2, Newton Raphson's method. Newton Raphson's method, they say that if xn is the initial approximation for the root of the equation, fx is equal to 0, then the beta approximation xn plus 1, this being subscripts, can be obtained from this expression here. Okay, so let's have it. So we know that xn plus 1, which is the beta approximation, is equal to xn minus fxn divided by f derivative of xn, where n is equal to 0, 1, 2, 3, and those values continue. Now we have that fx is equal to x power 3 minus x minus 1. Our fx is here, this one here, and remember this, very important. So we are going to get fxn. So after this we have here fxn. How do we get fxn? Just put subscript n, or in this function here, where there is x, put there subscript n. Now what we are doing, this here is a continuous function. Now putting smaller n as subscripts, we are discretizing our functions. We are discretizing it. And when it comes to differentiation, you don't differentiate this, you differentiate a continuous function. This one here, discretizing it means you're making it a constant. So if you happen to differentiate this, you are expected to get 0. But if you happen to differentiate this, you are expected to get a certain function or the derivative of this. So fxn is equal to, have xn power 3 minus xn minus 1. Next, we need to get f derivative of x. The moment you differentiate this, you are supposed to get 0. But it is very unfortunate. Our friends, after differentiating this, they get something, which is the derivative. That's wrong. So you first obtain the derivative here. So we are going to differentiate this function with respect to x. So we shall have this being 3, dropping the power, and then you reduce the power by 1. So we dropped the 3, we reduce the 3 by 1 to have this, minus, you drop the power, which is 1, 1, okay, then x power 1 minus 1, which is just 0, x power 0 here, and x power 0 is 1. So we have this, and from there we go ahead and get f derivative of xn. F derivative of xn, we just like for this one, we are going to plant their n's. So we shall have f derivative xn is equal to now 3 xn power 2 minus 1. And after getting these two expressions, we are going to substitute them here in the Newton Raphson's method for finding a beta approximation. So I will now have xn plus 1 being equal to xn minus, have this is f, I'm substituting in for fxn, and fxn is this here. So we shall have xn power 3 minus xn minus 1 all over. I will have, substituting for this, f derivative xn, which is here. This is 3 xn power 2 minus 1. The next step there is we are going to get the LCM. And you have to be wise on how to deal with a fraction here. So let's get the LCM. LCM is 3xn power 2 minus 1. So this divided by a 1 which is here, we shall have this very one times xn. So I have xn into bracket 3xn squared minus 1 minus, don't forget here, you have to put a bracket here. So we shall have xn power 3 minus xn minus 1. Next, we are going to open the bracket. So, opening the bracket here, I will have 3x power 3 here minus this time that xn minus, now this negative is entering here, xn power 3. This enters, becomes a positive. This enters, it becomes a positive there. Everything divided by, this is 3xn power 2 minus 1. So next I'm going to collect the like terms. This here will go away, and then this and that, you can see there, we are going to reduce. This is now going to have 2x power 3, then plus 1 divided by 3xn squared there minus 1. So this is xn plus 1. So this is the expression that we can be using to find the better approximation for the root of the other equation, where n is equal to 0, 1, 2, and they continue. Next, we are supposed to use this Newton Raphson's method to find the root. Use the Newton Raphson method to find the root correct to 2 decimal places. Now we discovered that the root actually lies between 1 and 2. That's where the root lies. Now these are going to act as the limits. Those ones are going to act, 1 and 2 are going to act as the limits, and we shall have to use 1 and 2 to find the initial approximation x naught. Initial approximation x naught is going to be the average of the two limits 1 and 2. Average, meaning you have this is over 2. So x naught is equal to 1.5. Remember, we are supposed to find the root, 2 decimal places. So this is 50. This is our initial approximation. Remember, also they gave us that it should be to 2 decimal places. I underlined this, showing you that it's very important. Now, this is going to determine the maximum error that we shall be having. Okay, so it is very important also to have it here. So we need to first of all include it here also. So we have maximum error is going to be a half times 10 power negative. Don't forget a negative. Let me check. Yes, negative n. But what is the n? N is the number of decimal places, and for us we have 2 decimal places, so this is power negative 2. So in terms of decimals, this will give us 0.005. Now our formula is here, and we have to use it to find the root, to do decimal places. Let us start. When small n is equal to 0, remember this is the formula, 2x power 3 small n here plus 1 all over 2xn squared minus 1, where this small n here is having from 0 up to they continue, takes on positive whole numbers. When n is equal to 0, put here 0, we shall have a better root as x1, 0 here, remaining with x1, being equal to 2, put here 0, it will be x naught power 3 plus 1 divided by 3 x naught power 2 minus 1. But what is our x naught? Our x naught is now 1.50. So I'm going to substitute here to get x1. x1 is now equal to 2 into bracket 1.5 power 3 plus 1 over 3 into bracket 1.5 squared minus 1. So when you compute very well there, when you press your calculator, you're going to get x1 as being equal to 1.3478. This is 4 dBs here. Now before we continue to something else, we have to get the error. Remember, this is the maximum error. So when we stop, we only stop if the error is less than the maximum error. Okay? Yes. Now let's get the error. Error, remember, is equal to the magnitude of x1 minus x naught. So I have 1.3478 minus 1.5 magnitude. So there, when you subtract, it is going to have 0.1522. Now 0.1522 is a value that is greater than the maximum error. It's greater than. This error here is very big. It's greater than what is required, 0.05. So what does that mean? It means we have to continue. Now next we are going to have smaller n being equal to 1. Remember here we started with 0. So when smaller n is equal to 1, we are substituting in that very formula. We shall have to get x2 being equal to now 2x power 3 plus 1 divided by 3xn power 2 minus 1. This is x1. Even this here is x1. But we have got x1. We've got x1. So I'm going to have x2 as being equal to 2 into bracket x1, which x1 is 1.3478 power 3 plus 1, everything over 3 into bracket 1.3478 power 2 minus 1. So here again, when you simplify, x2 is going to be equal to 1.3252. After that, we get the error, which is the magnitude of the consecutive roots. So here we had the initial root. We got error minus, the approximate value minus the initial root. Next is going to be now x2 minus x1. So we shall have to get 1.3252 minus 1.3478 and magnitude. So this error is equal to 0.0226, and this error here is greater than the maximum required error. So that means we are still continuing. So we need now to go to when n is equal to 2. When n is equal to 2, we shall have x3 being equal to 2x2 power 3 plus 1 all over 3x2 power 2 minus 1. So x3 is now equal to x2. We got it as 1.352. So we are substituting there. We shall have 2 into bracket 1.3252 power 3 plus 1, everything all over 3 into bracket 1.3252 power 2 minus 1. So x3, when you compute on your calculator, it's going to give us 1.3247. Next, before we continue, we have to check on the error. So error here is going to be x3 minus x2. magnitude, of course. So we have 1.3247 minus 1.3252 magnitude. This value is going to be 0.0005. Now you can see that the error here is less than the maximum error, which is 0.005. So the maximum error here is 0.005. And now the computed error here 0.0005, which is less than the maximum error. So from here we now make a conclusion and say therefore the root is 1.32. This is to 2 decimal places, and that's where we stop. You only stop after making sure that the computed error is less than the maximum standard error. Next is the exercise for you to test the knowledge which we have got here. Try this one. Number 1, using the range -2 less or equal to x less or equal to 5, determine the interval within which the real roots of the equation 2x power 2 minus 6x and 3 equal to 0 lie. Hence use the Newton Raphson's method to find the biggest root, correct, to 2 decimal places. Number 2, find the roots of the equations using Newton's Raphson method, NRM. Roman numeral 1, x power 3 plus 2x minus 2 equal to 0, correct to 3 dBs. Roman numeral 2, x power 4 minus 12x plus 12 equal to 0, correct to 2 dBs. Roman numeral 3, x power 3 minus 3x plus 4 equal to 0, correct to 3 dBs. And the negative root. So that one is very specific. Roman numeral 4, 3x power 2 plus x minus 5 equal to 0, correct to 3 dB. So this is our trial numbers. Let's try them out, and in case something is not clear, please replay the video back and forth again and again. You will get the knowledge as you do this. It is after doing math that you learn math. You don't learn math by just watching, you learn math by doing. That's why I endeavor to always provide the exercise at the end of every video, such that you can learn by doing. The psychomotor domain becomes activated. And again, don't forget to subscribe to my channel. It is educational, inspirational. Please share it with your friends and tell them about it. Thank you very much.